Love it. Nice to have you, sir.
To be like about 5'10".
No problem.
So if
No problem. Yeah. All right. See, we're gonna try to see if we can get started on time, so that we can let me know it's Friday. So everybody's wants to go home, spend time with their family. You ready up there, my camera crew? All right, so it's rolling. Okay. So, welcome to Join You Free Seminar Series 2018 in honor of this great man back there that's trying to get some munching right now. And today we want to talk a little bit about, an update to research that's been done here on earthquake forecasting in the last 4 years. And I think this year we really lucked out, and some interesting things are going to start happening as a result of all the work that's been done in the last 4 years. But also the Join You Free Seminar Series is an opportunity for some other good folks here, none of them is here, they're all hiding, to defend their thesis. So we start out here, just give a top level summary of what's been happening, and then students will come in and kind of dive in over the last 3 weeks here. They're going to tell you what those, more detail about some of the things I'm going to talk about in top level here. And then we always try to bring somebody from the outside. So we have this lady that I've known for a long time, very good physicist from Haystack Observatory, is going to come and talk. And then we get into the good stuff, right? People that are going to try to defend their thesis before they get out of here. So you have about very small senior class this time, just 3 people. So it should be fun. So my job today is to give you kind of a feeling for basically earthquake and then for forecasting. Of course, it's a gruesome picture here showing you what's happening when earthquake takes place. In January 2010, earthquake took place in Haiti, and in less than 30 minutes, 200,000 people died. Okay? And well, the country's still trying to get back on track. 2011, earthquake in Japan, 20,000 people died. So you can see the discrepancy now, right? So it's a problem of infrastructure, and because Japan has, more faults that are dangerous than Haiti, and they all basically build on water, and yet you have 20,000 and 200,000, right? So one of the questions that's been asked, because there used to be a time we're going to have a hurricane or a cyclone, and the stuff just come on us, and we didn't know. We'll take a town, complete cities out, and eventually we managed to have somebody, the weatherman that is our friend right now, lies to us from time to time, but tell us that something like that's going to happen, and we can run for cover, right? So the question has been asked, is that possible for earthquake? Is that possible? Is that going to be a time where we're going to be able to say, get out of town because an earthquake is coming? A lot of people think that's never going to be the case. Right? So for a natural disaster like that, it's very interesting that up to now that's not understood. You would have thought by now there would have been a lot of work done in the area, and would have known what's going on. And one of the reasons why that's not happening is because this is an area that requires a lot of input from many disciplines. As you'll see as I go through this, you'll see a lot of discipline comes in. It's not an electrical engineering thing. It's electrical engineering, physics, mathematics, chemistry, biology, you name it. So funny enough, when we're talking about capabilities that we have to predict earthquake, we have very good forecasting capability. And that's a dirty word to say, I'm going to tell you that within the next 20 years, there might be an earthquake of that magnitude in some area of the world. So we've gathered data on where earthquakes have happened, and we can tell you that, well, possibly in California, within the next 10 years, there's going to be an earthquake magnitude 7 to 9. But when will it ever happen? We don't know. And so the move that we've been trying to do is to move from forecasting, the probability of something happening somewhere, to prediction. That's a dirty word. If you go say prediction about earthquake, people start laughing at you, right? So what we mean by that is closer to some certainty, something that will rival what's happening with the weather right now, okay? Of course, we could still say it's happening and it doesn't happen, but at least if we say it 10 times, we hope that 5 times it will happen. That's already great progress, right, from what's happening now. So we want to move from the world of earthquake forecasting to the world of earthquake prediction. And we've asked the question about 4 years ago how to do that. I must tell you that I was kind of passionate about this problem since the earthquake happened in Haiti. I started working about this problem way before I came here. Started doing some things in it. And when I came here, I found a lot of good students that helped me get where I am today in this problem. And our approach, which has been not an approach that's been followed thus far by scientists in the field, is why not use everything we know about this problem? Why should we be fighting against each other, trying to shoot each other's work down about, okay, I know about change in the ionosphere, and somebody's coming and say, well, I don't think there's any change in the ionosphere. I know about change in pH concentration of water, and I'll say, well, I don't think there's any change in pH concentration of water. So it's been like that for the past 30 years, you know? So we say, well, we're going to move away from that model. We're going to use everything that's out there, okay? Everything that's out there. And so far, those are the things that we know are changing. We know that then when rocks are under stress as a result of moving faults, we know that they start creating a series of things like current, which generates a lot of other things, like magnetic field, potential changes. We know that the air chemistry at the surface of Earth is changing. We know the water in wells, proximity of the fault is changing. We know that the concentration of ion, electron above the Earth's surface is changing. And we know that what we call total electron content, which is a derivative of the electron density, is changing. So in this, we started here. We started in this too, here. At ENC, we mostly looked at these problems for the first 2-3 years, and then progressively started moving down this list. And now we've done work in every single one of these except air chemistry. I'm hoping this summer a brave student will come in and show me something about air chemistry, okay? And so when you have all that information, the idea is, so how do you use it? Because the big knock is that some of these parameters may be changing due to some other things that have nothing to do with earthquake. So how do you make the difference when they are for earthquake or not? And better yet, how do you put all this information together coherently under one umbrella? So we say we're going to have what we call a data assimilation and fusion platform for earthquake forecasting. What we mean by that is assimilate all of these data in a form that's suitable, and then fuse them. Basically, fuse them together to get one truth. Essentially saying that if one of these is lying to at one point, they cannot all be lying to you in the same day, at the same time. So if you can come up with something where you have a truth that's including all of these, then maybe you've got something that's better than what we started saying, right? So the first question we want to ask is, okay, moving along with this thinking, do we find some of the things in these lists that are promising? I mean, can we say that we've seen earthquake happen or going to happen, and then these parameters are showing something promising? So if yes, what is it that they're telling us that we can use? And if no, I mean, are we doomed, or what kind of approach do we take to go forward? So the primary purpose of summer research was to come in, take a bunch of students. I don't care what year you're from. I don't care what your background is. You come in, I throw you in an open wound, and I say, here's the problem. And here's what I think, where I think you can start. Very open forum. And you'll be surprised what we've been able to accomplish with that. Right? We started crawling kind of thing, trying to rob Peter to pay Paul everywhere to find money to support these students. And then next year we had a little bit more money. Next year a little bit more money. And now it's potentially we're going to have a lot of money. And I'll tell you that in a few minutes. You know, it's a good thing, right? Potentially. So, so we try to address these questions, give these students a very open forum to innovate, and you'll be surprised what you'll get out of freshmen, for example, you know, some very, very good things. All right, so at the same time, we try to tell them about the field in general, tell them what's been done in the field, and kind of let them pick where they want to contribute based on strength. So now, going back to earthquake, here's a kind of a snapshot. We look at this thing here. This is year that earthquake took place, and this is magnitude here. And the colors have to do with areas of the world. And, well, you see, when you look at this thing, you see red everywhere, right, at very big magnitude. That's Asia. Let's see. We see blue a little bit, but kind of 1965 was the last time we had a very big earthquake in Alaska. And we can see if we go down 1990 up to now, I mean, hasn't been a whole lot in North America. So, is that why we're not getting any money to do research in this field? No problem, right? We don't have to do anything. We're not going to have any earthquake in that part of the world. Now, when we look at another snapshot, we look, for example, and we see, well, here's Japan. Let's see. 2011, 1923, they spent $600 million in the 7.9 earthquake. And then they spent, what, $235 billion in that last one. Okay? What about North America? Well, okay, what was that? We spent $400 million here, and then 1994, 13 to 44 billion, right? So if anything else, I think. Is that adjusted for the dollar? Yeah. So if anything else, the money should be getting our attention, right? Spending a whole lot more money in very few number of years. So is there really a potential? If we look at the probability, they say yes, within 3 or 10 years, for sure, there's going to be an earthquake somewhere in California. We don't know when. And so if we have this kind of data, what can we do to prepare? So we know earthquake forecasting in here, but it's not going to tell us exactly what's going to happen. So the only way we're going to be able to prepare is earthquake prediction. Okay. So let me tell you quickly about earthquake for those of you that, well, everybody knows about earthquake, but trying to set up the stage for what I'm going to tell you later. You have 3 types of earthquakes. So basically the earth is made of tectonic plates. I mean, that's what the theory is. A bunch of plates that are moving around. They're free to move, but they move very, very slowly, millimeter per second. That movement is needed for the earth to breathe. And earthquake is when they move too much, right? So in the areas where they start moving too much, we call them fault. And in those areas, what's happening is you have pressure accumulating over a number of years. Okay? So here you have movement in this direction, so plates sliding across each other. They call that transform. You have plates moving away from each other, that's divergent. Plates moving away toward each other, that's convergent. As a matter of fact, this behavior is where volcano takes place. Okay? So the only time you have the earthquake takes place is you have a very violent shaking that's coming from the fact that in a fault, there's been accumulation of pressure, and all of a sudden it gives way. So you can think of earth crust having teeth. From time to time, the teeth are sliding, more pressure is building, and all of a sudden the teeth break. And that's it. Big movement, and things fall down, okay? With all the destruction that we showed you before. So the new direction is, can we really have all of these teeth getting entangled in each other without having any sort of energy buildup that we can measure. Okay? And in the process of these plates moving and hanging around each other, what's happening that we can measure before? So one of the first things we found is these stress that are being created in these faults actually start creating current. Okay? Start creating current, and we're going to discuss that. All of a sudden the rocks start behaving like crystals, and the crystals develop properties where they can give up electrons. We're going to look at some of that. So what we're trying to do is look at a series of a period of time before earthquake occurs. What can we measure, and what can we do with it after we measure it? All right, so that moves us into the world where before we used to have this big shock that happens all of a sudden. You didn't even know much about, you knew about aftershock, you didn't know much about this. Maybe you had some idea about some background activity, but now we're getting to the point where not only are we understanding the background activity very well, but we're also starting to pick up some of that energy, okay, within these things. Water chemistry changes, air chemistry changes, ground current, surface potential, electron ion densities that are changing, and EM fields that are being created as a result of all of that. So one of the other things we've seen also is that this class of precursors are living over a wide section of the Earth. They start from below the Earth, okay? So the water chemistry changes in the wells from 200 feet below the Earth's surface up to the Earth's surface. We have what's happening at the Earth's surface itself. You have air chemistry changes. It's air at the surface of the Earth that's changing, that's being ionized. We've got temperature. The surface of the Earth is getting warmer around this time. And then you start going up higher where your weather is taking place, what they call the troposphere, from 10 to 40 kilometers. There's a whole lot of things happening there. And then you go even higher in the ionosphere, and there's a lot of things happening there. So the challenge that we've had since 2015 is kind of, well, we started that way before, but really started getting going in 2015, is develop a model that describes these changes and build instruments that can measure them. So when we started doing this, we wanted to look at, like, for example, changing the magnetic field surface of Earth. There was a company that was working on this in California called QuickFinder. They were specialized in just magnetic field, and they called themselves QuickFinder. One of these instruments was being sold at $60,000. Certainly we couldn't buy that, right? So the philosophy is, okay, we're going to have the students build these things. And no matter how clumsy they are, let's see if we can measure anything with them, right? So that was that. So we started with that. So when you look at the whole picture, you have a series of things that start taking place down here. This is the Earth's crust. They start taking place up here and they move out. But most of the things causing it is out here, and we don't understand anything about that. I started writing about that in one of the papers I just published. I got pummeled by a lot of the people reviewing my paper because they told me I didn't know what I was talking about, and they were right. So, but I thought that I had to put this thing in context and say, well, this is where we think all this activity is going on. So there's a lot of work to be done here to kind of understand what's going on. But we are starting to understand a lot of things that's happening from over here, okay? So we call it starting point 1, 200 feet, and we move to the Earth's surface, we understand a bit more, and then we move out, we understand a whole lot. Actually, we are probably at the forefront of what's going on from the Earth's surface out. We've done more work in that area than anybody else, okay? I'm not joking, I'm serious, okay? You wouldn't think that, but that's true. So they're starting to come to us now when they're talking about what's happening at 40 kilometers up, because we can tell them some things that they can learn about. Okay, so that was basically summer presentations, and you're going to have a kind of a cross-section of all that. data assimilation platform. Caleb is going to talk to you about that. So that's where you take all the data that come together. People have worked on magnetic field precursors. We call all these things precursors. That means things that are happening before the earthquakes that we can see change in. And then water chemistry, Nick Burt and Joe McNeil worked on that, and TEC, Billy Malice worked on that. I worked on that too. And that's where we started basically. And then data assimilation platform back. So the very first thing is building a platform where you can bring all this together. Think about what's happening, how you bring that information real time. That's the first problem. That's what I talked about, data assimilation. And then you have to think about the fusion. So when we bring all this information in one platform, how do you fuse it together? So right now I think we've solved the simulation part. The fusion part is a different story, but we started to think about it in very, very, very good ways. As a matter of fact, we have a student that's thinking about making that his thesis. That would make my day, right, Caleb? That'll make my day. Okay. Yeah.
After you hit power, how does that figure in?
This is typically, we're thinking about solar power.
I'm sorry?
Solar power for it. That's what we're thinking here.
Okay.
Okay.
Now, how does it figure in with earthquakes, though, or does it not?
No, just powering this. That's not an input.
You want to have remote stations.
Right, right. Mostly remote station. As a matter of fact, the model that we're going to show you, I don't have a picture of it now. Somebody went and copied what we're proposing, okay? And that's part of what we're going to work on with a group very soon. So they're already copying this stuff. Okay, okay, so one of the fundamental contribution to earthquake forecasting had been done by a gentleman, a good friend of mine, Friedemann Fund. I met Friedemann in 2011 or so. I went to present a paper at in California, and I met this gentleman, and we've been working ever since. Very, very knowledgeable, but actually the people we're going to be working with, he came up with something very interesting, something that people never thought about before. This is a crystal, okay? This is an MgO crystal. I mean, it's, when you look at it, it's boring, you know, it's really not much about it, right? But when you look at in here, see this little thing here? This is water. As this thing crystallizing, it traps water within the crystal. Okay? And it so happened that it's very pure except for that. And it's used, people never paid attention to that, was never an issue until we started putting this crystal under stress. And all of a sudden, this thing that was very stable inside the crystal started reacting. Okay? So, surprised to most people that this thing was not as pure as we thought, and that in fact it contained impurities, dissolved water right inside the MgO matrix, and these impurities were ignored for a long time. Nobody paid it in mind because they were not very interesting. But what we found that's hidden in the structure is O2 minus that becomes O minuses. We call them pyroxes. Very stable, they don't have any problem. They live within the crystal, no problem, until we put them under stress. So these things are very normal. They stay in a dormant state within the crystal without having any problem until the crystal is put under stress. So here's one way to look at this. Okay, you have, this is when you have basically the crystallization state where this thing become the crystal plus water, this thing become hydroxyls pairs, and then what they become at the end is two O's, O minuses that are very stable that stay within the crystal without any problem. Okay. Now what's going to happen with these O minuses when you actually put them under stress, they're going to give an opportunity to give up a positive charge. Okay? Now let me go back.
What are you plotting horizontally?
Here's temperature.
Yeah.
Here's the amount of water that's included within the crystal as you go. Okay? All right, so typically we think about crystals from a semiconductor point of view, that, you know, there's a band gap between valence band and conduction band, which just means that if I apply a certain amount of energy across the crystal, I can get it to conduct. I can kind of break this gap, okay, basically. And sometimes you can even break it with just heat. You know, you can break it with heat. In the case of the insulator, that's when the gap is very large. So I'll have to apply a lot of energy across this to get something to jump, okay? And then you have the third part where I have an insulator that has an anomaly, and then this anomaly actually can get into a state that's higher than expected. That's the way actually this MgO behaves. It behaves in such a way that, you know, these O minuses can actually jump, and under stress, they just start behaving like this. In other words, the gap becomes much smaller, and then the stress allows conduction. Okay? That's how electricity starts being generated through this. So we call them epiconductors. They're not semiconductors. They're not insulators. They are things that are basically basic insulators until they are excited, until they are stressed. So Andrus was the first person to look at this thing because NASA had gone and conducted an experiment where they took rocks, subjected them to pressure, and showed indeed current is flowing. Okay? They spent about $300,000 to do that. So we challenged one of our students to do it for $300. You know? And I think we managed to do it for about maybe $1,300, I think, something like that. So we managed. So this is NASA's setup where they did that stuff, and they showed that. So here you have, this is stress, and this is electricity. So you start increasing the stress in the rock here using these multi-$100,000 presses that we couldn't buy. And then as you increase the pressure, then current starts flowing through the rock. So then you plateau, and then if you go down, we remove the pressure, currents go back down. Okay? Now we were able to repeat that experiment here. Okay? We're able to repeat that experiment here with, well, Andrus will show you, okay? With actually makeshift presses. We took a piece of granite, press it, and we measured current, right? It's a lot you can do when you're brave, and you're not afraid of anything. The worst that can happen is that you can fail, right? But, so we were able to repeat that experiment here. That was one person's senior thesis. Okay. The other thing that we found is not only can we create this current, but these positive charges travel to rock volume, through the rock, and outside of the rock volume, which was kind of interesting. Okay? And so that's how they start creating EM field. They start creating DC EM field, a varying EM field, potential at the surface of Earth, and so on and so forth. So they can actually flow out of the source volume and do all kinds of things, and you're going to see what happens when they do. But in the process of them traveling from the belly, from under the Earth's surface to the Earth, to outside, to the atmosphere actually, they do things like changing magnetic field. What you're going to see, for example, is when these things get to the Earth's surface, you're going to see small spike, very small, talking about nanotesla changes in the Earth's magnetic field that can be measured. So you need very specialized instruments to be able to see these kinds of things. That is as a result of that. So that's magnetic field per year here for a particular area, Loma Prieta. That was 7.1 earthquake, and you can clearly see the difference here where you have the anomaly right where the earthquake took place here. Very, very, very small thing. So you need to be able to measure, to build an instrument that can measure that. So last summer, we had a group of students working on that, and they'll show you what they found. Okay. The other thing is, as you start having these charges flowing from under the Earth's surface to the surface, to the Earth's surface, they end up ionizing the water under the Earth.
And what we found is that the pH concentration of the water is changing, conductivity is changing. Nick Burt and J.T. McNeil did some work on that, and they're going to show you some of these results. Okay? Now, what we found that was most interesting is when we started this way back, I think it's 2014, somewhere around that area, J.T. McNeil went and tried to look at whether or not we were going to have changes in water. So what he actually did, he took a piece of rock, he applied a voltage, typical voltage that a stress could create across it, and then he just looked to see whether or not there was change in pH in the water. And there were. But we said, well, this is manufactured, but we actually apply voltage, right? So what about if we actually took the rock, applied pressure in it, and see whether or not we'll see the same changes? So we built that over the last summer. This is Andreas here being a hero, drilling into the piece of rock, okay? And actually we took that, this is our makeshift press. You can see this is nowhere near what NASA has, but we were pumping this stuff to put pressure in there, but it's doing the job. And then those are the instruments measuring pH and conductivity. And those guys are going to show you what happened there. I can tell you the result is good. Impressive. Not even good, but impressive. Okay. Air ionization is the only thing we haven't been able to touch. We haven't found somebody that we can, anybody here in chemistry that was to tackle this problem? So chemistry students, we tried to take Bruna last year, but she got too busy. So what we're thinking is that you have mostly the air ionization is coming from oxygen, ionization of field ionization of oxygen. So the theory is that what you've got is here's your fault. You start creating these positive charges that flow up to the Earth's surface here, and then they create this surface potential. But at the same time, this surface potential can ionize this oxygen that's sitting around here, and then that's how we have these things propagating up, and then they disturb the ionosphere. So what you could see is that this positive charge is coming up. They hit this plasma here where they bring these charges down. I'll tell you that the ionosphere is basically a plasma. What that means is it's a semi-stable area with positive and negative charge are supposed to cancel each other out, but that's not really the case. You have more negative than positive. So what ends up happening here is that these positive charges are looking for friends in the ionosphere. Okay? And you're going to see that we see this behavior very distinctively. Actually, we're expert in that area, showing you what happens before an earthquake in that. But that's not my theory, actually. That's Friedman Fund. We haven't been able to really verify that's what's happening. This is a theory right now. But we can see this, but we don't know if this is being caused by that. See what I'm saying? We don't know that. But that's a good theory. At least it allows us to think about this problem. But we definitely see this ionosphere being pulled down before an earthquake occurs. We see that. Okay. So, Billy says, well, if I was to take an instrument that goes through this change here, I'm supposed to be able to see that. And that was his thesis. He tried to show what happened in changes of ion density by looking at GPS data. Right? Anytime anyone around the Earth, you can positively see 6 GPS satellites. And with these 6 GPS satellites, from where you are to where they are, you can measure position. And if you do it in 2 different frequencies, you can also measure the amount of electron that was along the line of sight from the receiver to the satellite. It's kind of interesting. So if you're sitting on Earth here, and you're looking at somewhere out here, because the GPS are way up, they're 20,000, they have very high orbit. We're talking about 1,000 kilometers, that's all we care about. But, so let's say around here, you're looking at what's happening around here with the ionosphere. Just the fact that you can see this line of sight, you can actually measure something along all these line of sights. There's a whole bunch of them, okay? So what you can measure is the number of electrons that is along that line from your receiver to your satellite, and you see it's a function of position and frequencies, and you can measure that. So Billy's going to show you a lot more about that. He's done much more than that, but I'll give you a kind of an introduction to that. In normal time, yes?
Go ahead. I'll ask it.
In normal time, we expect the electron, the TEC to look like a very nice curve like that. Very nice curve, you know, smooth, and it goes with the movement of the satellite. Here the satellite is far away. You see more because the line is longer. And as you come closer, you see less because the line is not as long, and you move away again, you see more. Very simple. But when an earthquake happens, the first thing that happens is this thing jumps out of nowhere. I mean, it's supposed to be a very smooth unit. It jumps. And then, after it jumps, and then it starts oscillating for a period of time. And then finally it settles down. Okay? So what we've been looking at is this behavior. When does it jump? And how long does it take to go through this oscillations, and then when does it go back down? And we try to correlate that with time of earthquakes, see what happens. So here's a little example of that snapshot of what I'm talking about. Of course, we did this thing in a plane. So we looked at maybe 100 different GPS receivers, and then we map this entire thing for Japan. This is the earthquake epicenter. This is the strength of the number of electrons that we can see. And so what we're looking at over these 100 different receivers sitting on the Earth of Japan is how this TEC is changing, number of electrons per unit of surface over time. This is what this thing looked like an hour 45 before the earthquake. Very high, unusually high. That's this. And all of a sudden, 1 minute before the earthquake, this thing goes from this to, let's say it jumps from, let's say, that's like a 2 unit down, and this is like almost a 0. Okay, that's like, what's that? An hour and 44 minutes. This is 1 minute after the earthquake. Interesting thing that happened here is that one of the biggest depletion that we saw in that pulling, you remember this negative charge being pulled down? One of the biggest we see is right looking at the epicenter. Right, looking at the epicenter is when we saw the biggest pull, okay? Which makes sense, right? If you look at this little picture that Friedman created for us. Now, 2 hours and 13 minutes after the earthquake, you have complete depletion. It's like almost all the ionosphere is completely gone, right? And then 2 hours and 45 minutes after the earthquake, it's coming back. It's more like what you should see. Still high here, still a little bit high, should be somewhere here, okay? So, this is the kind of things we think that we can use collectively with a bunch of other things to say that we think something is happening. All right, so now we're back to our good friend Caleb, who said he's going to put all that stuff together for us, right? So the idea is to take all this information, bring it together, and then see if you can come up with one truth. Caleb is going to talk to you a bit about that. All right, so when we look at this thing, it's certainly a very interesting problem because it's calling for so many people to contribute, right? And a lot of people working on this problem right now, and there's a lot of things happening. For example, in our case, we've made a lot of prototypes the student's going to discuss with you, published a lot of papers we're going to show you, and mostly where they're afraid of us, and that's why they're copying what we've done, is that we're doing this thing for dirt cheap, right? I mean, you can't beat that, right? We're doing magnetic field measurement for $40, right? We're doing water chemistry changes for, I don't know, $50. This guy's going to tell you. I mean, it's very, very cheap. So that's very interesting. The only most costly part of our thing is TEC. You need a lot of money to do TEC, but Billy says he's going to solve that problem for us. It's because the GPS, the dual frequency GPS are expensive. So if you can find another way of doing the same thing without dual GPS frequency, then. But at the same time, we're giving students very real-world experience in solving problems that are difficult, and it provided us with pathways to have relationship with outside organizations because we have something to tell. And certainly, we're looking to have pathway to granting organizations. So this is number of papers that we've written with students starting here to 2013. We can see we're marching up. Every year we're doing something. This is probably the biggest paper we published. Took me 2 years to publish this paper. Incredible how much they made me go through it. But at least it's out there now. It's published. And then now they have to accept that we've done something, right? We've done something in this area. We're not just talking about it, right? Of course, I've been in interviews. I've been interviewed before by some magazines and stuff. So we've made some noise to some degree with that work. Okay? Now, the noise has been vibrating. And so last year we have Friedemann, big at NASA, gave our students a presentation in the summer. So he gave a presentation, got the students all excited. But what he saw, that we had about 8 or 9 students from biology, chemistry, engineering, computer science, etc. He got excited about our group to see that we were able to do that, because he was getting good questions, right? Students were not coached, they were just giving him good questions, right? And so, from that time, we've started talking more about how can we work together. How can we work together? You have students that are working, they're working toward the same goals and objectives to build a platform. And so, one of the things that I proposed, he said, well, since I started working on this, because I was interested in what happened to Haiti, why not we try to convince the Haitian government to be the first country to put one of those things out there, okay? They told me they tried, that didn't happen. I said, okay, let me try. So I traveled to Haiti in December. I went and met with the Haitian government and the Ministry of Mines. I lucked out, I have to tell you. The guy that's the responsible for that program went to school with my brother. You know, there's a God somewhere, right? So I had a much easier time with him, so we had a good conversation. He didn't trust the people at NASA at all. You know, it says the people come to these small countries, they know we don't have any technology, they come in here just to steal our money, which is really the case most of the time. But, so I said, listen, I can promise you that this is not the case here. We really want to do something. So I told them 1 week after NASA traveled to Haiti, and they went to they didn't believe me. So they traveled, and they went to meet the Haitian government, and now we are working on the first pilot project to be put in Haiti as soon as possible. So the agreement is ENC and this group at NASA are going to work together to deploy 3 of such platform in Haiti in a triangle, so that we can predict inside the triangle, because we can do triangulation. And we asked the Haitian government to give us power 24 hours a day, internet 24 hours a day, security for the equipment, and then to let us bring the equipment in without paying any what do they call this? You know what I'm talking, any money. So we're working right now on sending them what we're going to do, timeline, what the expectations are. Once we do that, that should be done by this weekend. Then they're going to send us their contract that they're going to give us these things. And then we can start getting ready to go to Haiti. And I'm thinking within the next 2 months that should happen. So we're going with a number of students. We're going to try to take them for as less amount of days as possible. I want them with us down there to set up this equipment, become familiar with it. And yeah, the deal is, okay, if we get this going and we can show that this theory works, Haiti is going to put the big system. So what we get out of it is for the next 3 or 5 years, we get maybe 100 grand a year. That's what I'm asking anyway. I think it's small money for what we've done. So we get, for the next 4 years, 100 grand to do our own research, and we can support them any which way they want. Okay? But at least we're not scraping anymore to do some of the research, right? So we've got lots of supports over the years. Certainly Tim has been supportive, Linda, Larry, since he came in. Last year was very challenging because we were redoing this building, so we ended up hiding in the gym. So Brad was very, very, very gracious to let us use his multi-purpose room here. We stayed there. And of course, Dr. Friedemann for just starting to think about us, other than just a little small school that cannot do anything, and put us as part of the discussion, so I'm thinking for that. So that's my story, and I'm sticking to it. You know, I went very fast so that I can make it easy. So now I'll take any questions that you have. Any questions about any of this thing, this game? So any questions?
So, this is not you getting up at 4:30.
Ah, no, that's my brother.
Your brother.
Yeah, that's my brother.
Well, maybe you ought to take his,
That was my brother that was doing that.
I just have a quick question for that.
Yep.
I convinced myself.
You want me to go back?
You have a model back a few slides where the charges in the ionosphere separated. Yeah. Go for it. One.
Yep.
So, I was wondering, my initial question was, I was wondering if you could use the GPS data and triangulation to actually see the separation, but I kind of convinced myself we can't.
Yeah.
But,
Yeah. So this thing requires, thank you, Robert, for coming. Yeah. This thing requires a lot of GPS.
yeah.
That's part of the problem, right? Japan has a lot of money. They have what? They have 6,000 of them on the surface of their surface. So what we're trying to come up with is a way of doing this cheaper by having maybe a few of high but dual frequency and some at single frequency and see whether or not we can have the same, but we don't know. We haven't tried triangulation. Don't know. We haven't tried that. So, yeah. Yes. Yeah. Yeah.
What technique I'm looking at, you're looking for positively charged oxygen here.
Yep.
And so one thing you can look at is the magnetic susceptibility
Yeah.
of the
Okay.
oxygen should have 2 up there.
Okay.
In the ground state, when you knock off an electron, it goes 1. So if you design a pass through and you splash it on it with a magnetic field
Yep.
on the plate, you should
Yep.
be able to detect that.
So if you could write that up for us, for a student.
I haven't done it yet, but the same thing here too is
Yeah.
your primary one is oxygen, but
Yep.
nitrogen can do the same thing.
That's right. Nitrogen could do the same thing.
Nitrogen is more interesting because it's not magnetically susceptible
Right.
until you ionize.
Yeah.
So that one's a little bit more of a low-hanging fruit. It
Yeah.
has